All right, here's the floor, here's the wall, and here's our ladder leaning up against the wall. And they say that there's an angle here. I'm going to call it theta. And they're asking what is the minimum angle where it doesn't just slide out. So we know that we need enough static friction right here to keep it from sliding out. So let's just draw some force vectors right on top of what we draw in here. We were just talking about the friction that keeps it from moving to the left. So the frictional force must be like this. There's a friction. We also have to have a normal force here, holding the ladder from burying itself into the floor. So there's our normal force. The ladder has a mass, so that means it has weight. The weight is going to be located right in the center of the ladder. That'll be right here. We'll call that mg. And the wall up here is pushing on the ladder. Now normally walls can have a horizontal and a vertical component to the way they can push on something like this. But the problem specifically says that there's no friction on the wall. That means it can't push up or down. Imagine if the wall was infinitely slippery. It could still push this way, but it just can't push up and down. So the wall force is directly horizontal like that. I'm going to call it W for wall force. And those are all the forces we have in this problem. So in my usual way, I start out by doing the force balancing equations to see if I can get away with not doing torque, because torque is hard. So I'm going to do an x and a y equation with force balancing. In the x direction, we only have two things. We got the friction force going to the right, and we have the wall force going to the left. And that's it. And it's not moving, so that's going to be equal to 0. Then we look at the y forces. All we have is the normal force and mg. Normal force is up, mg is down. They have to add up to 0. And we also know that friction is equal to mu times the normal force. Now, this is static friction. And static friction is not always equal. Sometimes it's less than mu times the normal force. But they're talking about the limiting case here where it's almost going to start sliding. So that's why we can say it's equal. And we can put all of this stuff together, but even with all of this stuff, we're not going to be able to figure out the angle. But I think these equations are going to be useful later. But I see that in order to get a torque, in order to get an angle, I'm going to have to bring torque into it. So let's see. Before I can do my torques, I need to choose the center of rotation. I've got, and I just need to get the angle in there somehow. I don't have to be fancy. And I've got 1, 2, 3, 4 forces. I'd like to do my torque equation with as few forces as possible. So I think that I'll make the center of rotation down here and get rid of both of these. That'll be easier. So now I'm going to draw my lever arms for the other two forces. The first force is this weight force. Its lever arm is half the length of the ladder. You see that? Halfway. For the wall force, my lever arm, all the way up there, is the whole length of the ladder. So far, so good. Now I need to look at my angles. This angle here between this lever arm and the weight force, that angle there is part of the triangle where there's a right angle. This is the angle we want, and theta's down here. So that angle in there is 90 minus theta. Get it? Now we need the angle up here. So we need the angle between this lever arm and that force, that angle. Well, I think that if you look at the wall force and we look at, for example, the friction force, the ladder is going like this, right? And this angle here is alternate interior with this angle there, right? And this angle there is theta, so this angle is also theta. So that guy is theta. All right, finish the geometry. Now I'm ready to write the torque equation. Remember, the torque equation is going to be the total torque equals 0. I've only got two of them. I've got this one pointing one way, this one pointing the other way. Doesn't matter which one I make negative because it's not moving. So I'm just going to make the first one positive. So remember, torque is always RF sine theta, right? So my first torque from the weight force is going to be the R, which is half the length, the F, which is mass times gravity, times the sine of the angle, which is 90 minus theta. Okay? The other one, which I'll make negative, the lever arm is the whole length of the ladder. See this whole lever arm here? The force is the wall force, and then we have sine of theta. And this whole thing has to be equal to 0. So that's the equation I need to solve to find theta. Now I looked through here and they told me the length of the ladder, so that's pretty good. We don't know the mass of the ladder. I hope that's going to cancel out somehow. We're looking for theta, so that's okay that we have theta here. There's the length of the ladder again, but oh, the wall force, I don't know what that is. Now's the time I'm going to go back and use these force equations to figure out what the wall force is. So this first equation tells me that the wall force is equal to friction. This equation tells me that friction is equal to mu times the normal force. This equation says that the normal force equals mg. So that tells me that the wall force is equal to mu mg. That's going to be useful. I'm going to take this and put it in there. And when I rewrite that, I get 0 equals 1/2 length of the ladder, mass times gravity, times the sine of 90 minus theta, minus L mu mg sine theta. Now I can factor a bunch of stuff out here. I can factor out L, M, and G. So I can do L, M, G, parentheses, 1/2 sine 90 minus theta, minus mu sine theta. And this is equal to 0, right? So I can divide both sides by LMG because I know that none of them is equal to 0. And that tells me that, I forgot that parentheses, that 1/2 sine 90 minus theta minus mu sine theta is equal to 0. Now I'm going to do something clever. The sine of 90 minus theta is equal to the cosine of theta. So now this says 1/2 cosine theta equals mu sine theta if I add mu sine theta to both sides, right? And then if I divide both sides by cosine and divide both sides by mu, I get 1/2 mu is equal to sine theta over cosine theta, which is also equal to tangent theta. So I've run out of room over here. If tangent theta is equal to 1/2 mu, I can solve for theta.